Hello and welcome to EC3030. So in this video lecture we will introduce the concept of Cmos inverter, and then we will look into the basic operation of this inverter. Alright, so on the left I am showing the symbol of a logic inverter, and in a logic inverter you have the input on the left and output on the right. And if the input is a logic level 0, you would get a 1 at the output, and on the other hand, if you have a 1 in the input, you will get a 0 at the output. And in the form of a truth table, the truth table will look like this. So physically, a CMOS inverter is implemented by a circuit that looks like this. So this is the circuit implementation of a CMOS inverter, and in this CMOS inverter you essentially have a P MOSFET and an N MOSFET which is connected like this, and the CMOS, in this CMOS the C stands for complementary, and this complementary means that you have an N MOSFET which is complemented by a P MOSFET. And what happens is that if the input voltage here is 0 volts, then at the output you will get a voltage of VDD, where VDD is the voltage that is shown here, and essentially that is equivalent to this one, because a logic level 0 is represented by 0 voltage and a logic level 1 is represented by a voltage of VDD, where VDD is the power supply voltage. And similarly, if the input is equal to VDD, then you will get a 0 voltage at the output, and which is equivalent to this row in the truth table. So one thing you will clearly notice here is that the symbol of the NMOS that we are using is a little bit different from the symbol that we have used previously, and basically we have an extra connection here. And similarly for the PMOS, there is a similar contact like this, and this contact is called body contact. Now let me explain why we are showing this specifically for the inverters. Alright, so in this slide we're showing the N MOSFET with a body contact, and what you can clearly see here is that we have an extra P plus contact here. Alright, so if you look at this N MOSFET, the body is P type, then you have the source here which is N plus type, and the drain here which is N plus type, and just next to the source you have this P plus contact, and this contact is what we call the body contact. And you will also note that this body and the source are shorted, and this voltage is what we call the VSN. N stands for N-type MOSFET, and the fact that they're shorted is essentially shown by this arrow over here, or this connection over here. Now essentially this body contact and the fact that it is shorted to the source means that whenever we are talking about the gate voltage and drain voltages and the operation of this N-type MOSFET, we will now start referring to all these voltages with respect to the source voltage. So let me explain what we mean. So for example, here in this slide we have the source of the N-type MOSFET grounded. In other words, VSN equals to 0. Alright. So now what will happen is that, and the IDN is the current that is flowing through the drain of this MOSFET, or IDN is the current that is flowing through this path. And what we have seen before is that, so for example, in this case, the threshold voltage is 1 volt. So let's plot the Idvd characteristics. So in the y-axis, we will have IDN over here. Now in the x-axis, previously we were plotting Vd. Now what we are going to do is, we are going to say, okay, it's not Vd, it's rather Vds, to emphasize the fact that the drain voltage is with respect to the source voltage. In other words, we'll say that Vds n equals Vdn minus Vsn. All right. So now we have seen before that, okay, so when Vgs is smaller than 1 volts and the threshold voltage is 1 volt, so when Vgs n is smaller than 1 volts, the device is off, for example, for which the current is 0. Now if we keep on increasing Vgs n, the saturation current will also increase, and this is something that we have seen before. Now what is VGS? So VGS basically means the gate voltage with respect to the source voltage of this n-type transistor, n-type MOSFET. And in this particular example, because VSN is grounded, so it is equal to 0. So if VGSN is 4 volts, then VGN is 4 volts. And similarly, when VGSN equals to 3 volt, the VGN is 3 volts. And similarly, these two cases. Now this is very trivial. Now there is not much of a difference as to what we have seen before for n MOSFET without body contact, meaning that in this case VGSN and VGN are equal to each other simply because we have put VSN to 0, or the source contact to 0. However, this is not the case when we have a P MOSFET. Alright, so let's look at a P MOSFET with a body contact. So this is the schematic diagram of how a P MOSFET looks like. So the body is N-type, the drain is P-type, P plus type, and then we have source which is also P-type, P plus type, and then next to the source we have this body contact for the P-type MOSFET. And note that just like the N MOSFET with the body contact, the source and the body are shorted, and this is what we denote by VSP, which stands for the source voltage of the P-type MOSFET, and then the gate voltage is VGP and the drain voltage is VDP. Alright, so now let's look at the current that flows between the source and drain. Now for a P MOSFET, this region is, this terminal is the source and this terminal here is the drain, and the body contact, because it's shorted to the source, this is how this connection is drawn here. And note the current, the way we are drawing it, the current flows from the source to the drain. Alright, so in this case what we are going to do is we are going to plot the drain current IDP, the current that flows from the source to the drain, as a function of the voltage of the source with respect to drain, which is VSDP, so which is equal to VSP minus VDP. Alright, so in this case the threshold voltage is minus 1 volts. Now what does it mean? It means that when the gate to source voltage is smaller than minus 1 volts, when the gate to source voltage is larger than minus 1 volts, the device will be in an off state. So what does it mean? So this is in this plot, what we can clearly see is that the when the VGSP is larger than -1 volts, the current is basically 0 here. In other words, you can say that when the gate voltage respect to the source voltage is say negative 0.5 volts or even 0 volts or 0.5 volts, this device will be off. Alright. So as you decrease the gate voltage with respect to the source voltage below -1 volts, then you will start getting current through the device. So for example, when VGSP is -2 volts, you get this much of current. You then decrease VGSP to -3 volts, you get larger current. And when you go to VGSP equals to -4 volts, then you go to then even higher current. All right. And note, VGSP is VGP minus VSP, which means the gate voltage with respect to the source voltage of the p-type MOSFET. Alright, so let me first correct a typo here. So here VSDP is VS minus VSP minus VDP. Alright, okay, so in this particular case, what we have done is that we have set the VSP, the source voltage of the p-type MOSFET, equal to VDD, which is say 4 volts. Alright, so now let's see what happens. So the VGSP is equal to VGP minus VSP, and VSP equals to 4 volts. So for each value of VGSP, we can calculate what is the value of VGP. Alright. So, and if VSP is 4 volts and VGSP is -4 volts, we get VGP equals to 0 volts. Similarly, when VGSP is -3 volts, we get VGP equals to 1 volts, and when VGSP equals to -2 volts, we get VGP equals to 2 volts, and when VGSP is larger than -1 volts, we see that VGP is larger than 3 volts. Alright, so what does it mean? It means that if we have a p-type MOSFET where the source is at 4 volts, then this device will conduct a certain amount of current when VGP equals to 1 volts, and as we now increase VGP to say 1 volts, the current will decrease, the saturation current, and if we increase the gate voltage to 2 volts, then the current will further decrease, and when VGP is larger than or equal to 3 volts, the device will be off. Alright, so that's kind of opposite to what happens in an N MOSFET. In an N MOSFET with the source grounded, if we had increased the gate voltage, the current would have increased. On the other hand, in a P MOSFET with the source voltage at 4 volts, as we increase the gate voltage, the current actually decreases. Alright. So now this is how the inverter looks like. Okay. So we have seen the individually how the N MOSFET looks like and the P MOSFET looks like, and to implement this inverter circuit over here, this is how the physical device looks like. Right. So here this is the P MOSFET, this is the P MOSFET, and this is the N MOSFET. This is the source of the N MOSFET, and this is the body of the N MOSFET. So let's say SN and BN, and these are shorted and they're connected to the ground, and this is the drain of the N-type MOSFET, and this is also the drain of the P-type MOSFET, and they are connected to each other, and this is the output voltage. So just so we're clear, so this is VDP, this is VDN, this is VSN, and this is VGN, this is VGP, this is GN and GP, and this is SP. So here you have the source of the p-type MOSFET, and this is the body of the p-type MOSFET, and the source and body are shorted and connected to the power supply voltage VDD. And finally, the gate of both of the devices are connected to each other, and this is this connect this gate connection is what we call equal to VI. All right. Okay, so now let's see how it works as an inverter. Okay. All right, so I have plotted the same thing over here. So just so we are sure, VI is equal to VGN equals VGP. So this is VGP and this is VGN, and they're both equal. All right, and the MOSFET, N-type MOSFET has a threshold voltage of 1 volts, and the P-type MOSFET has a threshold voltage of -1 volts. All right, so let's first see what happens when Vi equals to 0. Okay. So when Vi equals to 0, then our VGN is equal to 0, so which means that it is represented by this green curve over here, and when it's represented by green curve, basically it means off. So basically whatever the drain voltage is, which is the drain voltage of this guy is whatever be the drain voltage is, there will be no current flowing through the device. So essentially this looks like an open circuit. On the other hand, uh, the gate voltage of the p-type MOSFET is is 0. So it essentially means that this p-type MOSFET is in an on state. So if it's an on state, you can represent it a certain resistance, and this is actually on state essentially means that it is a low resistance. So as a result, you can think about this circuit, this current path, as a series combination of two resistors. Now the N MOSFET is an open circuit, and the P MOSFET is a small resistance. And then clearly you can see that in this case, if you just apply voltage divider law, then you will see that the output voltage here will become equal to 4 volts, because this is open circuit. And this is essentially what you're seeing here is that if the input is 0 volts, you get an output of 4 volts. Or if the input is a logic level 0, the output is a logic level 1. And what is essentially happening is that because when your input is 0 volts, your N MOSFET is turned off, and as a result, the V0 becomes equal to VDD, and it is as if with a 0 volts, this transistor action is such that this output voltage is pulled up to the VDD, and as a result, this transistor, the p-type transistor, is also called the pull-up transistor. All right. Okay. So now let's see what happens when your input voltage is 4 volts. So if the input voltage is 4 volts, then the 4 volts, then essentially means that VGP is 4 volts, and if VGP is 4 volts, then the current through the p-type MOSFET, whatever the drain voltage is, will be 0. In other words, it's in off state, and as a result it's an open circuit here. The P MOSFET is an open circuit between its source and drain terminals when the input voltage is 4 volts. On the other hand, the N MOSFET, when the input voltage is 4 volts, its gate voltage VGN is equal to 4 volts, basically means that it is in on state. So you can represent it with a resistance like RTN, so resistance of the transistor, N-type transistor, RTN, and then you can just think about this current path as a combination of two resistors, where the resistor corresponding to the P MOSFET is open circuit, and as a result, what is just looking at this resistor divider here, you can just see that in this case the output voltage will be equal to 0. In other words, when the input voltage is 4 volts, the output voltage is 0, or if the input is a logic level 1, the output will be a logic level 0. Now again, in this case, what you can see is that when the input voltage is 4 volts, essentially the voltage output voltage is pulled down to 0. So the action of the N MOSFET is such that it tries to pull the output voltage to 0, and as such this N MOSFET is also called the pull down transistor.